Abnormal molar masses. Now, what is abnormal molar mass? There are 4 types of colligative properties, and using those colligative properties, molar mass of unknown solute can be calculated. For example, consider delta Tb. Delta Tb is elevation in boiling point. This is equal to Kb into m, where m is the molality of solution. Writing the formula for the molality of solution, this becomes Kb into W divided by molar mass of the solute. W is the weight of the solute, m is the molar mass of the solute, then weight of solvent in kgs. Now if Kb, weight of solute, weight of solvent is known, then knowing the value of elevation in boiling point, molar mass of the solute can be calculated. As can be seen, keeping all other quantities constant, delta Tb is inversely proportional to molar mass of the solute. Means delta Tb is kind of colligative property. Means if the value of delta Tb increases, then the experimental value of the molar mass will be less than the actual molar mass, which is calculated from the formula. And if delta Tb value is less, then the experimental molar mass will be greater than that calculated from the molecular formula. These molar masses, which are either greater than the one calculated from the chemical formula or less than the one calculated from the chemical formula, these are known as abnormal molar masses. Now, what is the reason behind abnormal molar mass? The reason behind abnormal molar mass is association or dissociation of the solute. Some solutes dissociate in solution and some solutes associate in solution. So, for ionic compounds, when dissolved in water, for example, potassium chloride, this is ionic compound, this is when dissolved in water, it dissociates into potassium ion and chloride ion. So, after dissociation in solution, potassium and chloride ions are present. So, if we start with 1 mole of KCl, then 1 mole of KCl dissociates to form 1 mole of potassium ion and 1 mole of chloride ion. 1 mole of KCl gives 2 moles of particle. So, undissociated KCl is only 1 particle, but when it dissociates, it gives 1 mole of potassium ion, 1 mole of chloride ion. So, total number of particles become 2. 1 mole of KCl dissociates to give 1 mole of potassium and 1 mole of chloride. So, total number of particles become 2. So, if we ignore interionic interactions, 1 mole of KCl in 1 kg of water would be expected to increase the boiling point by 2 into 0.52, which is equal to 1.04 Kelvin. See, if one particle increased the boiling point by 0.52 Kelvin, then 2 particles will increase the boiling point by 2 into 0.52 Kelvin. Because colligative properties, they depend on the number of particles. They do not depend upon the nature of the particles. Instead, they depend upon the number of the particles. So, here the number of particles is increasing. So, colligative effect is increasing. So, elevation in boiling point is increasing. For one particle, elevation in boiling point is 0.52 Kelvin. For 2 particles, elevation in boiling point is 2 into 0.52 Kelvin. Now, if we did not know about the degree of dissociation, we could be led to conclude that the mass of 2 mole particles is 74.5 gram and the mass of 1 mole of KCl would be 37.25 gram. See, molar mass of KCl is 74.5 gram. Now, since KCl is dissociating to form 2 mole of particles, we would have assumed that 2 moles of particles are weighing 74.5 gram. The weight of 2 moles of particles is 74.5 gram. So, from this, weight of 1 mole of particle will be half of 74.5 gram, that is 37.25 gram. So, due to dissociation, the actual molar mass is 74.5 gram. But because of dissociation, the experimental molar mass will be 37.25 gram. That is, experimental weight is less than the molar mass calculated from the chemical formula. This brings into light the rule that when there is dissociation of solute into ions, the experimentally determined molar mass is always lower than the true value. See, the experimental weight, the one calculated from colligative property, will be 37.25. The actual molar mass is 74.5. So, the experimental weight is less than the one calculated from the chemical formula when there is dissociation of the solute, when the solute undergoes dissociation. Now consider acetic acid in benzene. So molecules of ethanoic acid or acetic acid, they dimerize in benzene due to hydrogen bonding. So two particles, they dimerize and change into one particle. So number of particles is decreasing, it is just becoming half. This normally happens in solvents of low dielectric constant. In this case, the number of particles is reduced due to dimerization. Association of molecules is depicted as follows. This is the association of ethanoic acid due to hydrogen bonding. Now, if all the molecules of ethanoic acid associate in benzene, then delta Tb or delta Tf for ethanoic acid will be half of the normal value. Both delta Tb and delta Tf are colligative properties which depend upon the number of particles. So, if the number of particles decrease, then colligative property will also decrease. For example, when the number of particles is 1, colligative property is 1. When the number of particles is decreasing, means it is becoming half, the colligative property will also become half. So, in case of dimerization, number of particles is becoming half of the original number of particles, means 2 particles are becoming 1 particle. So, number of particles is becoming half, so colligative property will also be half. That is, value of delta Tb and delta Tf will be half. Therefore, the molar mass calculated on the basis of delta Tb or delta Tf will be twice the expected value. When delta Tb becomes half, molar mass becomes double. Such a molar mass that is either lower or higher than the expected normal value is called abnormal molar mass. In 1880, Van 't Hoff introduced a factor I, which is known as Van 't Hoff factor, to account for the extent of dissociation or association. This factor I is defined as I is equal to normal molar mass divided by abnormal molar mass, observed colligative property divided by calculated colligative property, total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation. Here abnormal molar mass is experimentally determined molar mass and calculated colligative properties are obtained by assuming that the non-volatile solute is neither associated nor dissociated. If we assume that the non-volatile solute is neither associated nor dissociated, then that is the calculated colligative property. In case of association, value of I is less than unity, while for dissociation it is greater than unity. For example, value of I for KCl, which undergoes dissociation, it is close to 2, means I is greater than 1 for KCl, while the value for ethanoic acid in benzene, which undergoes association, I is less than 1, that is 0.5.